Okay, good morning. So, in my previous class, I was looking at this carbonate sensor. Okay. You take this cryptand and then make a di-copper complex, di-copper cryptate. This di-copper cryptate, the distance between them, distance between the two copper and the distance between this carbonate and carbonate moiety, this distance is optimum. So, that carbonate forms a very strong complex with copper. So, this is the situation. Now what? Now, we add to that coumarin derivative, coumarin. So, when we add coumarin, okay, the coumarin binds to this copper. Now let me remove this carbonate first. There is no carbonate. I have only, there is no carbonate. I have only coumarin and this copper 2 cryptate. So, this coumarin binds to this carboxylate. Okay, coumarin derivative is called coumarin 343, I believe. Coumarin 343. Okay. So, this carboxylate will bind to this copper 2 centers, and since it is a negative and copper 2 is positively charged. So, therefore, there is a strong attraction to bind. So, carboxylate, oxygen, so it binds, and then this coumarin. So, therefore, when we excite coumarin, it goes to excited state, but no fluorescence. Why? Because of these paramagnetic centers, it comes down to the ground state by non-radiative pathway. Okay. So, so when there is nothing, only coumarin and this copper 2 cryptate, no fluorescence upon excitation. But now I put carbonate in the system. So, carbonate binds much better than carboxylate. Okay. Carbonate binds much better than carboxylate. Carbonate binds much better than carboxylate, oxygen, oxygen, and then this oxygen. So, it binds much better, is a CO2 minus, and it binds to copper 2 centers, 2 copper 2 centers. When it binds, so the carbonate kicks out coumarin outside, coumarin goes outside. So, now when I excite it, it gives strong fluorescence, because there is nothing to quench. So, because copper is already engaged. So, it gives you a strong fluorescence. So, therefore, this is another mechanism. So, I encourage you to make different types of mechanism. So, let me tell you some other mechanisms, okay, some other types of mechanism. This particular compound, this also happens to be coumarin. Let me draw the picture. Picture is very important here. Okay. And now, this is coumarin. Okay. Okay. Now, this we took an aldehyde group. Okay. Here is one aldehyde group. Let me first write the aldehyde group CHO, and then I put an amine similar way. Let me draw. I told you that this is very important to draw sometimes. I cannot do away with cartoon. Okay. 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 ये तो नहीं रहेगा. Okay. Okay. Amine here. NH2. Okay. I told you that most of our cryptands are made by condensation of amine with aldehyde. So, when you condense them, you get you get an H2O out. So, H2O out means you get this compound. You get this compound CH double bond. Okay. You get this compound, okay, double bond N. So, this is called imine linkage, imine. Okay, this imine linkage we generate, and this takes about half an hour. So, you cook them, you get this. So, these are two, this is 1, this is 2, they are 2 coumarin derivatives. Two coumarin derivatives. Okay. So, now what happens is, what happens when I excite it? You know, when you excite a molecule containing double bond, okay, suppose I excite a molecule, just an example I am giving. Here I put Me means methyl group, and I put hydrogen here, and then I put hydrogen here and methyl here. So, this is a cis. When I excite it, if you excite, then it comes like this, and stop excitation, then it Me goes here, hydrogen, Me comes here, it becomes trans. It becomes trans. Why? Because it can rotate. Why it can rotate? Double bond cannot rotate, but when we excite it, double bond becomes single bond momentarily, and as soon as it becomes single bond, it rotates. Okay. So, similar case here also happens. If I excite this molecule, then it got excited. Now, it has to come to the ground state, because the molecule is already excited. In this case, in this particular case, it comes to the ground state by way of rotation along this bond. It becomes single bond momentarily, and then it can rotate. So, all these things, double bond to single bond and rotation, requires energy. Where from this molecule will get energy? from the excited state. So, excited state energy is now transferred. Excited state energy is now transferred in making this happening rotational. Okay. So, therefore, my fluorophore does not give any fluorescence. Now, this moiety is very specific for a very important metal ion, biologically important, magnesium is very important for magnesium 2 plus, and it is very specific. Now, I am going to put magnesium here. Okay. If I put magnesium here, then what will happen? Magnesium comes here, it makes a bond, it makes a bond, it makes a bond, and its anion X. So, it makes a bond. So, now if I put magnesium 2 plus, it will come here and makes a bond here, bond here, bond here, and X, suppose magnesium chloride. So, this will be chloride. Okay. All right. So, now if I excite this molecule, because magnesium is already holding this, let us see if I can explain to you. Magnesium, so this is oxygen, and magnesium is here bound. So, if this wants to rotate, my oxygen with respect to 1, suppose this is rotating, means this is stable, this is not, but this is rotating. Then what will happen? This oxygen and this oxygen has to go up, but if it is bound to metal, okay, then it cannot go. That means rotational degrees of freedom is checked by magnesium. So, if I put magnesium 2 plus ion, only magnesium goes here. If you have calcium, magnesium, strontium, sodium, potassium, all the transition metal, they do not go, only magnesium will go. So, it is very important, specific, and it goes and stops this rotation. Because it stops this rotation, so when I excite my molecule, it has no other de-excitation pathway. Okay. So, this is how this is another. So, when you are making this making a design, you must stop the de-excitation pathway in the molecule. So, I have stopped de-excitation of the molecule from excited to the ground state. How? Through coordination with magnesium. And so, therefore, when I excite it, it will give a strong fluorescence. So, I am telling you so many words, but actually what happens? I take this compound and throw magnesium and then excite it, very strong fluorescence, very, very strong. And magnesium, you know that magnesium does not have any color. So, we cannot easily detect, let alone concentration. So, this is a simple case where very simple design, these two compounds are available, aldehyde and amine is available in the market. So, we bought this, in half an hour we got the result, and then send the paper, within 15 days paper accepted in a great journal. Okay. And that has been a very popular in citation, very high citation. So, I encourage you all, whenever you do the fluorescence, not only PET, but there should be many other mechanisms which you must look into. Then I am telling you another mechanism very important. Suppose I have this compound. So, different types of mechanism Means your first idea is, if I excite, is there any pathway that it can deactivate? That is what question you will ask. If there is any pathway that this excited molecule will come down to the ground state, then no fluorescence you will get. Okay. So, therefore, I have to stop that pathway. For example, another example I give you. So, I encourage you all to design H. So, I am writing this now. Okay. Okay. All right. So, this is the compound. This is my compound. Okay. How it works? This is this compound, and this is your coumarin. So, it is a coumarin derivative. Okay. When we excite it, when we excite this molecule coumarin, then what happened? This thing, this phenomenon happens. This phenomenon will happen. Just carefully look, this is a solid and this is a dash dash line. So, that is important, or maybe I will use color. Yeah, I should use color. I am putting the dashed line in blue color, fine. Now, when I excite this coumarin, this thing happens. This is 5, that is why it is not working. Good, bad. So, this molecule, now look at carefully what I am doing. Okay. So, what I have done? When I excite this coumarin when it was excited, then this hydrogen transferred from oxygen to nitrogen. That is why with nitrogen now I have a solid line, and I have a dashed line with oxygen and hydrogen, between hydrogen. Earlier was nitrogen and hydrogen had dashed line, but oxygen and hydrogen had solid line. That is why it was a hydroxo compound, but now it is a nitrogen is now bonded to hydrogen, okay, and of course, this is now 1, 2, 3, 5. So, I will change it also. So, what happens? There will be some changes. I told you that valency cannot change. Okay. So, valency cannot change. This and this. So, it becomes like this. Okay. So, from enol it becomes a keto, and this is known as excited state proton intramolecular proton transfer, ESI-PT mechanism. So, whenever there is ESI-PT mechanism, that means there will be hydrogen transfer from oxygen to nitrogen, and then from enol it becomes keto. Okay. So, all these things require energy. So, that means when I excite this coumarin, it gets deactivated. And how it gets deactivated? Because there are so many transfer is going on here, from here to here. Okay. So, because this transfer, hang on, I have not made the compound yet properly. This is there. Compound must be there, it cannot have any mistake. Okay. All right. So, now what happens? Because of this ESI-PT mechanism, hydrogen got transferred. So, ESI-PT stands for excited state intramolecular proton transfer. So, that means at the excited state, this proton transfer takes place intramolecularly, and therefore, when I excite, no fluorescence. Now, I add zinc ion. If I add zinc ion to this, then what happens? If I put zinc ion here, okay, if I put zinc ion there, I will go a little bit up. ऐसे करते हैं. Okay. Then this happens. I put zinc chloride, okay. Then I put zinc chloride in the beginning without excitation. So, this could be my one of the chlorines. Okay. I put zinc here before excitation. I put zinc. So, there is no zinc, I excite it, nothing happens. Now, I put zinc and I get this structure. Okay, I get this structure. My molecule this should be little bit closer there, because this is a bond, single bond, but looks very far. Not like that, this is my poor drawing. Okay. So, I can do simply here, this one we got, that means hydrogen is gone and you bind zinc here, okay, here, same structure as this is same identical. Okay. So, क्या होगा? So, what the problem? Now, the thing is hydrogen is not there. So, there is no question of excited state proton transfer. So, in absence of excited state proton transfer, if I excite this coumarin, I see a very strong fluorescence. What problem will happen if I put nickel 2 or copper 2? See, nickel 2 or copper 2 may make paramagnetic. Okay. Nickel 2 may make octahedral, which is paramagnetic, and copper 2 is always paramagnetic. So, therefore, paramagnetic quenching will take place. So, that is why zinc, and this is zinc specific. So, therefore, I got another system. It depends upon, here it was stoppage of double bond rotation, and here it is stoppage of proton transfer, intramolecular proton transfer, ESIPT mechanism. So, therefore, both these work on the principle that, I mean all of the cases, that when we excite, then we have to stop deactivation pathway. From ground state to excited state, I have to stop deactivation pathway. Only then I will see strong fluorescence, because it has to come down giving fluorescence. Okay. So, this is another mechanism. ESIPT is a very popular mechanism, and this double bond was done by my student, and this is also a very fine, very nice, okay, very easy, and very quickly it was done. So, I encourage you all that when you do sensors for metal ions or anything, or anions or neutral molecules, you please look at this principle, that I have to stop deactivation pathway, I have to have whether I have a PET possibility, all these things, if you do that, then you can get good result. Thank you very much.